Okay, to help you with number 17, you're asked to make this function x cubed all over x minus 2 squared to have a power series representation for it. Let's see what we can do here. I think I even gave you a little bit of a hint. We can recall one of the most famous. This is where we start so very often. The geometric series can definitely be used to help us here with 1 over 1 minus x. What I made a little hint on to help you is to start here with this power series, but in regard to actually starting off with 1 over 2 minus x. You can see if you compare that original denominator down here, that's at least relatively close. And if we were to factor out a 1/2, you could see that we'd be left with 1 over 1 minus x over 2. Now, what that means is, following from up above, we'd have a 1/2 out in front. But everywhere where we have an x, including inside of the sigma here, we can make a substitution. And by the way, we even have the absolute value of x less than 1. We're about to do a little substitution of x over 2, you can see. So this x, everywhere where we have an x, it's replaced with that x over 2. And including in the sigma here, we'll have this x over 2 to the n. And we'll say inside of sigma, we're going to have x over 2 to the n. Even inside this absolute value, we'll have x over 2 is less than 1. And just cleaning this up a little bit, we can see that this is actually going to be, as we distribute a 1/2, we'd have 1/2 plus x all over 4, plus here you'd have x squared over 4, but we're going to actually have another factor of 2 down below. That would be 2 to the third. Here, this x to the n, we'd have x to the n. We have 2 to the n down below, but we're adding in another factor of 2 because of that 1/2. So what does sigma look like? Well, we're going to have x to the n all over 2 to the n plus 1, because we're going to have 1/2 out in front of that sigma as well. And here we can say that this is the absolute value of x. Really, multiplying by 2, we'd have absolute value of x less than 2. In other words, we have a radius of 2 now for this convergence. Well, this is honestly what we have with 1 over 2 minus x. That's our function. But if we do a little bit of work off to the side, the reason why I made this suggestion to work with 1 over 2 minus x is because we can take a derivative of that. That's really 2 minus x to the negative 1 power. And if we took this derivative, we'd bring down a negative 1. We'd have 2 minus x to the negative 2. Then by the chain rule, we'd multiply by the derivative of negative x, which is negative 1. We can see that this actually is a derivative of 1 over 2 minus x quantity squared. But I also gave you another hint that 2 minus x quantity squared is actually going to be equivalent to x minus 2 quantity squared. When you're squaring a difference of 2 terms, order really doesn't matter. So what we can do right now is just say, let's take a derivative. We just saw that on the left side we'd get 1 over, and I'm going to write x minus 2 quantity squared. And what will we get as we work this derivative out? Well, the 1/2 is going to be gone, that constant. The derivative of x over 4, that just becomes 1/4. And then here we could say bring down a 2. We'd have 2x all over 2 to the third. We could say plus dot, dot, dot. Derivative of x to the n. We're only taking a derivative with respect to x. So we bring down the n. We'll have nx to the n minus 1. Still have this 2n plus 1 in the denominator. But as we take our derivative of sigma, I hope you remember that we lose a term. This now goes from n equals 1. We'll have n, x to the n minus 1, all over 2 to the n plus 1 power. We still have the same radius of convergence. We'll have the absolute value of x less than 2. Now, if you look at the top left corner of the screen here, you can see we're so amazingly close to what we're looking for. We just need to have x to the third placed up on top. In other words, we have to multiply everything by x to the third. So that's going to be our final step in this process, as we multiply by x to the third everywhere. Every single term gets multiplied by x to the third. This is going to become 2x to the fourth, all over 2 to the third. Multiplying by x to the third, you're going to add the 3 and the n minus 1. So what's that going to leave us with? Well, an n plus 2. I hope you will agree. And inside of sigma, we're going to get this as well. We'll have n equals 1 to infinity. This becomes n to the x to the n plus 2, all over 2 to the n plus 1. And again, something I've been saying quite frequently, and I always say this, you can check if your sigma is correct by letting n equal 1 and see if you are generating this series in the middle here. Like if you were to let n equal 1, you'd get 1 times x to the 1 plus 2, which is x to the third. Down below, 1 plus 1 is 2. 2 squared is 4. You could keep going here. You can see this is generating what we'd like to have. This answer, by the way, is 100% accurate and correct. That being said, it's very likely, when we check the back of the book, that Professor Stewart doesn't write this down. Instead, it's very likely, and it's important regardless of how he writes this, that we know how to make a change here. We could say, you know what, our counter could begin at n equals 0. And the way we compensate is we have to do some counterbalancing. We made our counter go down one step. That means everywhere else in this formula inside of sigma, we must increase by one step. So wherever we see an n, add one more to it. N plus 2 will become n plus 3. Down below, this n plus 1 would become n plus 2. And again, I bring this up again, that this sigma, we could very well check if this is accurate by plugging in n equals 0. You could see you would get 1/4 x to the third. You could say, hey, what if we let n equal 1? You can quickly confirm that you'd get 2x to the fourth all over 2 to the third. It's also why I didn't even reduce that. You can see immediately what's happening. But that would be your power series representation.